Hello, and welcome to Section 3 of Part 2 of the training course on the demographic evaluation of age and sex data. In Section 3 of Part 2, we're going to cover the evaluation of sex data from demographic inquiries, such as censuses or surveys, and then move on to look at the assessment of age and sex data using information from multiple inquiries, for example, successive censuses. We're going to cover an introduction to synthetic cohorts, give you an introduction and an exposition of how to go about doing graphical cohort analysis using multiple censuses or surveys, and end off this section, Section 3 of Part 2, with a discussion about the evaluation of growth rates. Turning to the evaluation and assessment of data on sex collected in a census or a survey. Typically, these are not subject to much error, and certainly to much less error than is encountered with respect to age. As a binary variable, male, female, the scope for reporting or content error of sex data is much more limited than it is in the case of age. Coverage error, however, may be far more significant and far more identifiable and far more of concern in the analysis of sex data. In many societies, female children are differentially omitted with respect to age than male children are. The sequestration of adult women in some societies might lead to them being under-enumerated or undercounted or under-surveyed. And the presence of migrant workers in the population may have a material bearing on the sex data for that population, particularly if that migration in or out is highly sex specific. When we are looking at the evaluation of data on sex, we use two principal metrics. The first, the sex ratio, is the number of males per 100 females at any one age or in any one age group. And so that would be given by dividing the number of males by the number of females at that age or in that age group and multiplying it by 100. Another metric is the sex ratio at birth, which is the number of male births per 100 female births in a given period. And so that would be calculated by dividing the male births in that period divided by the female births in that period and multiplying again by 100 to give an expression of the number of male births per 100 female births. Typically, the sex ratio at birth can be derived from data from a civil registration and vital statistics system, or sourced from the full birth histories contained in a demographic and health survey data. The sex ratio at birth might also be calculated using census data, using information on the sex of the last born child in the year before the census. However, not all censuses routinely ask that question, in which case the sex ratio at birth would have to be evaluated and estimated using CRVS or demographic and health survey data. There is a third metric, masculinity ratios, but we ignore these because they provide very limited information relative to the sex ratio. But just for completeness, we would define the masculinity ratio as the proportion of the population that is male at one age or in any single age group. But our focus today is going to be on the calculation of the sex ratio and the analysis of those data, as well as looking at the sex ratio at birth. As noted in Section 2 of Part 2, there are several questions which one needs to ask in any form of graphical analysis of demographic data. The first is to ask, what are we looking at? What does the plot show? What are the axes, horizontally and vertically, X and Y? What are the quantities being plotted? Are they numbers or are they proportions? Does the plot show what you think it does? Prior to any analysis, we have a pre-existing understanding of what we would expect to see in a plot of age or sex data. If the plot really doesn't conform with what you would expect it to show, then it might be an indication that the data have not been extracted properly. Once we are satisfied that we understand what we are looking at, we then look at the plot and ask ourselves, what are we seeing? Are there anomalies, differentials, discrepancies, possible ideas of sources of error in the data? And we look at what characteristics exist in that plot which we have before us. We would then move on to say, how might we explain what we see? What explanations might be invoked to justify what we are seeing? Or might we have to eventually conclude that what we are seeing is the consequence of data error? How might we test those explanations, and with what data? So we're going to use the same 3 countries which we used in section 2 of part 2 of this training workshop, which is data from 3 censuses sourced from the UN Statistical Division Census Database. And those censuses are that conducted in Bahrain in 2010, in Nepal in 2001, shown in red, and South Africa in 2011, shown in green. What we have in this plot is, along the x-axis here, ages by single years of age. You can see the highly erratic plots for each of the 3 countries, showing that those are data by single years of age. And going up the y-axis here are the sex ratios per 100 women. So going up this vertical axis is an indication of the number of men per 100 women revealed by those 3 censuses. Now, our prior expectation is that in most human populations, the number of male births is roughly equivalent to the number of female births, and male and female mortality in early childhood and adolescence are at very similar levels. And so we would tend to expect to see sex ratios very close to 100 for children and young adults up into early adolescence. However, at the other extreme of the age range, we also know that male mortality is much heavier than female mortality, that men at any age are more likely to die than women. And what this means is that at the extremes of the age range, at extreme old ages, we would expect to find far more old women than we find old men. And so at any single age, you would expect the sex ratio to be less than 100. Revealing that there are fewer than 100 men for every 100 females at those ages. We can see in the data for South Africa, the green line, that the number of men for every 100 women remains very close to 100 up until about age 35 or 40, and then falls off. As I discussed in section 2 of this part of the workshop, South African male mortality is much higher than female mortality in the country, and this is shown by this diminishing sex ratio, whereby by age 75, these data would seem to suggest that there are only about 50 men for every 100 women. By contrast, if we look at the data for Bahrain, we see that the sex ratio rises very rapidly to about 260 men for every 100 women, round about the age of 25 or 28. And then falls off to a lower level at age 40, around about 170, before plummeting to 100 men for every 100 women, around about age 65. And those sex ratios then remain roughly constant, bouncing somewhere around about 100 at ages after that. This is somewhat surprising because we do expect male mortality to be heavier than female mortality. And the fact that the sex ratio doesn't clearly drop below 100 after age 60 in this population is probably an indication that elderly women have been differentially underenumerated in the population. Turning to the data for Nepal, which is shown by the red line, as we saw in section 2 of part 2 of this training course, that the number of men relative to the number of women between ages about 15 and 40 is less than the number of women at those ages, and the sex ratio is therefore below 100. As we discussed in section 2, part 2, that is probably explained by male outmigration from Nepal to neighboring countries for economic reasons. Somewhat curiously, however, after age 40, the sex ratio in Nepal is consistently above 100 up until about age 75 or so. And that would imply that there are more men per 100 females than one would expect, given the burden of mortality amongst men and women. And so this might well be an indication of differential underenumeration of women in the Nepalese census, certainly up to age 75, and would be a matter of something which has to be explained and examined very closely. We can see in the Nepalese data that the sex ratio does fall below 100 after about age 75 or 80 and shows a downward trend, in other words, implying that there are more women for every 100 men as age increases. But the scale of that decline is somewhat surprisingly low, and would also again point that even at these extreme ages, women might have been differentially underenumerated in that census. But as we did with the age data, it's also important to look at the sex ratios in 5-year age groups. We can see along the x-axis here, the 5-year age bands, 0 to 4, 5 to 9. For the Bahraini data, the open interval starts in the age 85 to 89 interval, which is why it's marked with an asterisk, whereas for the women in the population of Nepal, that open interval begins in the 95 to 99 age group. And looking at the data by 5-year age groups removes much of the noise which was evident in the previous graph, but still shows the same essential characteristics. We can see that the sex ratio in all 3 countries remains very close to 100 up until about age 15 or so, and then starts to diverge. We've already seen the impacts of labor migration into Bahrain, and this is evident here in the highly distorted sex ratios up to age 65. But this decline after that, again, would seem to indicate that women are being differentially underenumerated in that census. In the Nepalese data, the labor outmigration of young adult men is evident in the sex ratios below 1 there, implying that they're men who were not counted, probably because they were in a different country. But after age 35 and all the way up to almost age 80, that sex ratio is either very close to 100 men for 100 women, or in fact indicates more men than there are women in the population. And that is certainly surprising and would be a cause for concern that perhaps elderly women have been differentially omitted from the Nepalese census. And again, that is something which should be requiring urgent and careful attention. By contrast, in South Africa, again, the sex ratio remains relatively constant before falling very gradually. And certainly here at the extremes of the old age, we can see something rather curious, which seems to suggest that at the very extreme age group, age 100 or more, that there are far more men per 100 women than there were of people in their 90s. And that is almost certainly an indication of age exaggeration and differential underenumeration of women in that census. And that should also be subjected to further inquiry. The second metric which we discussed and mentioned at the start of this section of the training workshop was the sex ratio at birth. And if possible, one should seek to examine the time trend in that sex ratio at birth. We'd expect the sex ratio at birth in most human populations to be largely constant, and in almost every human population should be in the range of 100 to 105 male births for every 100 female births. Values more or greater than 105 male births for every 100 female births might well be an indication of perhaps sex-specific terminations of pregnancy, resulting in a surfeit of male births, female infanticide postpartum, or non-registration of female births. And certainly values greater than 105 should be subjected to very careful investigation as to what might be causing that. A further investigation into the sex ratio at birth may be to examine the sex ratio at birth not only over time, but also by the age of the mother. Because we don't expect the sex ratio at birth to change very much in a given setting from over time, these sex ratios should be roughly constant by the age of the mother. And again, if they're not, It might be a possible indication of sex-specific termination of pregnancy, female infanticide postpartum, or the non-registration of female births amongst women of particular age groups. So these are data showing the sex ratio at birth in South Africa from 2000 through to 2020 from the South African civil registration system. Along the x-axis, we have the time going from 2000 to 2020, and up the vertical axis, we have a truncated series. It only starts at 99 and ends at 102.5 of the sex ratio at birth, as shown by our civil registration system in every year of births occurring in each of those years from 2000 to 2020. Please note that this lower bound of the vertical axis is not at 0. If it was, this line would come out and would appear to be more or less flat. But for purposes of investigating these data, we actually want to look at it and be able to pick out and discern trends far more carefully. Hence, we only start the plot of the sex ratio at birth at 99 boys for every 100 girls. What is curious about this plot is that it would appear to show that from about 2000 through to 2010, that the sex ratio at birth increased from about 100.4 male births for every 100 female births to about 101.6 male births for every 100 female births. In the context of South African history, that is probably unlikely. And this is likely then to reflect that over time, there has been differential completeness of reporting male and female births, and that perhaps in these early years, male births were being differentially not reported to the authorities. This might be, amongst other reasons, because male stillbirths tend to be more prevalent than female stillbirths, certainly in South Africa, and therefore, if stillbirths were not being properly recorded in the data, or deaths immediately postpartum were not being properly recorded, that this sex ratio at birth might be explained by a changing pattern of completeness by sex of neonatal, perinatal births by sex. After 2010, from 2010 to 2020, however, that pattern is still subject to minor annual variation, but is typically between 101.5 and 102 male births for every 100 female births, which conforms with our expectation in the South African population. On this slide, I'm showing how one might be able to look at the sex ratio at birth by the age of the mother. Along the x-axis here, we have the mother's age at the time of birth, and on the vertical axis, we have the sex ratio of number of male births per 100 female births, running from 95 to 105 male births, relative to for every 100 female births. And what we have extracted here are data from our census, which is shown in the blue line, showing of births in the year before the census, because the question was asked in the South African census of 2011, what was the sex of the last born child? And on the red line, we have the sex ratio at birth for covering exactly the same period from October 2010 through to September 2011 of the sex ratio at birth as revealed by our civil registration data. And certainly what one can see here is that there are two factors at work. Amongst the most prevalent childbearing ages from 15 up to 35, the civil registration data shows an almost constant sex ratio at birth of just under 102 males for every 100 females. And yet after that, ages 35, 40, and 45 to 49, that sex ratio at birth declines, which again would seem to indicate that male births are being differentially underreported in our civil registration vital statistics data. When we look at the census data, however, in general, the opposite effect seems to be happening, is that at certainly ages up to age 40, it would appear that more male births are being reported as having occurred in the last year than female births, and at a level much higher than that indicated by the civil registration data, which would seem to suggest that there's some sex-specific bias in the reporting of the sex of the last born child in the South African census data. Curiously, we also see that the sex ratio at birth declines for the two oldest age groups to below 100. And that is probably also a reflection of underreporting of male births amongst older women, as there's no biological reason necessarily why, as women get older, yes, the sex distribution of their children should be changed to be more heavily weighted to that of young girls. So to conclude, in terms of the evaluation of age and sex data from a single data source, this step is always the very first one taken in evaluating data from a census or a survey. It provides a quick and inexpensive indication of the overall quality of your data and provides an indication of where specific problems in the data may be found. These exercises, however, almost always still have to be rooted in historical context of understanding, for example, patterns of labor migration in Bahrain or Nepal, and prior understanding of the demographic trends in the population being analyzed. The major limitation of these kind of investigations is that it is usually not possible to identify or quantify separately the magnitude of coverage and content error in the data. And so the identification of coverage error usually requires some other gold standard population estimates, say from a population projection or an international series of population data, to try and get a better sense as to what might be the explanation for what one is seeing in the data. In the second half of this video, I want to look at using data from multiple inquiries, multiple censuses, multiple surveys to assess the quality of age and sex data. In addition to conducting all the investigations covered so far, one can do so much more with data from multiple inquiries. What we're going to be covering here are matters relating to synthetic cohorts and graphical cohort analysis, intercensal growth rates, the derivation of cohort survival ratios, and balance equation analysis. We'll also be making mention of information derived using analytical projections, for example, the comparison with data from other populations, projections, and series of population estimates. The first of these investigations using multiple inquiries is to introduce you to the idea of a synthetic cohort. And the underlying logic of a synthetic cohort is relatively straightforward. When we have data from two or more censuses or surveys of the same population, we can use the data from those multiple censuses or surveys to gain further insights into the quality of the census and survey data. The essential idea is simple. If two censuses are conducted exactly 10 years apart, well, then the count of those aged, for example, 30 to 34 at the time of the second census, should be the count of the population aged 20 to 24 in the first census, other than for the effects of mortality and migration over the last 10 years in that cohort. And so the idea underpinning graphical cohort analysis is to compare actual cohorts over multiple censuses or surveys. And we would expect that the size of each of those cohorts should decline between the inquiries due to the effects of mortality. In general, international migration is typically very small relative to the size of the population and can usually be ignored. But remember context. Context is vitally important. Remember, in the data which I presented, for example, from the Bahraini census of 2010, where labor migration was extensive relative to the domestic population. And therefore, one needs to bear in mind that this observation, that in general international migration is very small and can usually be ignored, does not hold in each and every situation. But where we can analyze those data and not have to worry about the impact of international migration on the size of any given cohort, the age structure revealed in each census or each survey should follow the same pattern in the absence of errors in those data. An important advantage of being able to do this is that it is then possible to evaluate the effects of extraordinary events or other distorting factors by following actual cohorts over time. And the example which I'm going to be using in this section of the training workshop is data from Mozambique, a Southeast African country, using data from its 1997 and 2007 censuses. As with the previous section, the spreadsheet underpinning these data is also provided with this video, and so you can look at it and look at the calculations and the way in which the analysis was done in your own time, following the calculations in Excel. On this screen are the data from the two different surveys, censuses. This first panel over here contains data from the 1997 Mozambican census for males and females and the total population, and the data from the 2007 census, females and males and the total population. And here the observation really is that this population of 878,429 females aged 10 to 14 in the 1997 census will be the same population of women who are then aged 20 to 24, 10 years later at the time of the 2007 census, and likewise for males and the total population. So as three examples, these orange shaded cells here for the 10 to 14 in 1997 will be the population aged 20 to 24 in 2007. And the green cells, 15 to 19 in 1997, would be the 25 to 29-year-olds in 2007, and the 25 to 29-year-olds in 1997 would be these pink shaded areas. Sorry, I could correct myself. The 20 to 24-year-olds in 1997 will be the pink shaded cells aged 30 to 34 in the 2007 census. And if you're eagle-eyed, you can start even just by eyeballing the numbers. Say there are some curiosities in these data. Not least of all is that you can see here that these 878,429 females in 1997, aged 10 to 14, have suddenly become 986,526 females, aged 20 to 24, 10 years later. In general, because we expect cohorts to diminish over time due to mortality, either that must reflect significant in-migration of people who are 10 to 14 in 1997, who are now 20 to 24 in 2007, or it might be an indication that this count of young women aged 10 to 14 in 1997 was too low. And really the point of the exercise of graphical cohort analysis is to start being able to examine those kind of contradictions and discrepancies in somewhat greater detail. So what we have here in this plot is the plot of the number of women by equivalent birth cohort, which means regardless of which census they were enumerated in, the blue line being 1997 and the red line being the 2007 census, is that we're saying for women born between mid-1992 and mid-97, in the 2007 census, there were approximately 1.2 million such women, whereas in the 1997 census, there were close to 1.4 million such women. And so along the x-axis, we have different birth cohorts arranged in reverse order. So these are women who are very old at the time of the censuses. These are women who are much younger at the time of the censuses. And going up the vertical axis is that count of the number of women by equivalent birth cohort. And what we can see looking at these data is we can see here that in 2007, there were more women reported as being born between mid-1982 and mid-1987 than was shown 10 years earlier in the 1997 census. Over an extended range there afterwards, however, there are fewer women in 2007 for any given birth cohort than there were women in 1997 in that birth cohort. And in many ways that is to be expected, not least of all because of the effect of mortality over the 10 years between the two censuses. We can do the same exercise for males by equivalent birth cohort. So this is an identical plot to the previous one. And whereas there were these points of discrepancy here amongst the females aged 10 to 14 at the time of the first census and 20 to 24 at the time of the second census, that is not evident in the data on males. And so that is starting to lead one to an assumption or a tentative conclusion that perhaps there was a problem with the enumeration, certainly, of the young girls in the earlier 1997 census, which was not evident amongst the population of males. A second way of thinking about growth of population change between two different inquiries is to rearrange the demographic continuous growth equation. This is an equation which relates the population, the N, big N, at some time, time 2, to the same population at some earlier point in time, at time 1. And it says that the population at time 2 is the population at time 1, growing exponentially, that's the function E, at a rate R for a number of years between time 2 and time 1. We can rearrange that formula to leave only R on the left-hand side of the formula, and we get an expression for the growth rate to be the natural log of the ratio of the population at time 2 to the population at time 1, divided by the amount of time elapsed between the two times, time 2 minus time 1. And an important check is to assess the plausibility of these growth rates and whether they conform to known or expected trends over time. We can take, for example, data from Botswana censuses in 1991 and 2001. And we can take the population of males, 639,378 males in 1991, which had grown to a population of 813,625 males at the time of the 2001 census. Likewise, the number of females in the Botswana population grew from 693,000 in 1991 to 867,000 at the time of the 2001 census. And using the information on males, those two numbers there, we can get a measure of the growth rate in the male population between 1991 and 2001, which is revealed to be 2.41%, and equivalently 2.24% for females. In general, in the absence of extensive migration and sex-specific migration at that, we would expect these two growth rates of the male and female populations to be very close to each other, but they will not be identical because the time trend and change in mortality might be different for men and women. In other words, that male mortality might have improved faster than female mortality, leading to more males relatively to females surviving over that 10-year period, and that would result in a higher growth rate of the male population relative to females. But these two numbers should be broadly equivalent to each other. I'm going to switch now to present the data to show the calculation of the data from the calculation of the sex ratios on the Excel spreadsheet from the three countries, Bahrain, Nepal, and South Africa. And you will be able to investigate how these sex ratios are calculated. Going down here in column A are the sex ratios by single years of age, and those are derived from the tabulation of the age data on the age sheet, which was used as the initial input into the earlier investigations we did in the previous section. And so columns B, C, and D present the sex ratios by single years of age for those three countries. And equivalently, in columns F to I, we have the sex ratios by 5-year age groups, and the plots are shown further along the graph. Likewise, on the sex ratio at birth tab, the data presenting the sex ratio at birth in the South African data is presented there in case you'd like to look at it and get a feel for how those calculations were done. But it's in the calculation of the graphical cohort analysis that I want to give a little greater explanation. Again, these data come from the UN Statistical Division tabulations. The hidden cells off to the left here are the data by single years of age. And as I showed in the previous section of this part of the training workshop, I showed how you could derive data by 5-year age groups from single year data. And that is what these panels do. What we then seek to do is we then recast these ages, those say age 10 to 14 in 1997, and we say if they were aged 10 to 14 in 1997, on average, they would have been aged 12 and a half at the time of the 1997 census, because halfway between age 10 and 15, and therefore, if the census was conducted at the mid-year of 1997, well, then that represents the birth cohort between 1987, starting in 1987 and ending 5 years later. So what we have here then in these data are the data by different birth cohorts for the Mozambican data. And the graphical cohort analysis basically takes those tabulations and then plots them as we saw in the graph over here. When we're looking at intercensual growth, again, these are data from Mozambique, again, from those two censuses, 1997 and 2007. We can calculate the overall population growth rates over the entire period, the total population at any point, using that logarithmic formula explained. And what I want to really draw your attention to here now, because we'll be looking at the cohort survival in the next part of the training workshop, are the somewhat varying rates of population growth by age in these populations. And we can see here that particularly at the older ages, from ages 17 onwards, the growth rates between the 1997 and the 2007 census are running at somewhere between 3.5% and 4% typically per annum. And the question you need to ask yourself is that this might well be an indication of rapidly improving mortality between the two censuses, or alternatively, if there's no external evidence to indicate rapidly improving mortality, that the quality of one or the other censuses might have been deficient, either in terms of undercounting elderly people in 1997 or overcounting those aged at older ages in the 2007 census. As always, as we end another session of these video trainings, if you have any questions or comments on this material, please email me, thomas.moultrie@un.org, and copy it to the ESCAP CRVS team, unescap-crvs@un.org. And I'll do my best to answer questions either by return of email or in the first plenary session on the 27th of May. I look forward to meeting you all then, and thank you very much for joining me.